Okay, so this is the final presentation for the challenge in which we were required to build a catapult and then analyze the motion of the projectile through programs like MATLAB. Okay, so first, the objective of this challenge was that we were able to design first the catapult and then also to develop a program that was able to calculate what the position of the catapult would be using Euler's method, considering that we had fixed initial velocity and with different masses for different projectiles. And the importance of projectile motion in physics is that it's like the representation of some of the most basic physics laws, like the Newton laws, and also that its uses are multidisciplinary. Like it's not just for math, physics, and science, but also other areas used such as sports or astrophysics or biology or
Well, now we have for a catapult. For its design, we use like screws and nails, two nuts, some wood, the lid of a container, and a clean rope. This catapult has dimensions of 40 times 50 centimeters and has an arm of 60 centimeters. To operate this catapult, we have a system of torsion. So to make this work, two holes were made in the opposite sides of the face to pass the clean rope from one side to the other, interlacing the arm. So this will later allow us to make the torsion by twisting by tying the two pieces of wood.
Okay, so we are going to talk about the theoretical background on these catapults. Here we can see all the movement in the velocity vectors that the projectile has in the half time of the projectile. Here is the acceleration on x, that is 0 meters per square seconds. Then velocity on x, that is velocity initial cosine of degrees. Then there's an equation that means the range of the catapult by multiplying the velocity on x. And then multiplied by t seconds, that is the total hang time that the catapult has, and plus the initial position in x, supposedly or assuming that the position is 0, right? In this example. In general, we can describe that is an influence of a projectile launched by initial velocity in degrees and is affected by the gravity. Here we have the general equations like here, but more explaining hang time, range, and maximum height. And these ones you could also came up with them with these equations. Here I have the acceleration in g, that is gravity. Gravity is minus 9.8 meters per second squared. And then the velocity in g, this one is minus 9.8 times the seconds in the hang time. And then plus the initial velocity in j, and then here I can get where is the position in y on the hang time or any specific moment in time. Both of them are with any kind of seconds. Here I have the minus 4.9 t squared plus the initial velocity in g times time, and plus the initial height. Here in the initial height is about 60 centimeters of the catapult, and these are like explanations of what I talked about. And this is also taking into account that we are neglecting the air resistance. So there's like a theoretical perfect equations. And lastly, the velocity magnitude, we can take it with the initial velocity on g squared and the initial velocity in x squared, and that having the root of that sum.
Okay, for hypothesis and predictions, we need to establish that we couldn't have like a very strong hypothesis because we having the coefficient of torsion of the climbing rope. So these hypotheses are that the range of the projectile increases as torsion increases. This is the same with the initial velocity, because when we have more torsion, more force are created to pull the arm of the catapult. Also, the optimal angle from maximum reach is 45 degrees. This was calculated because when we have like a sine of to calculate the range, we need to sine of 2 theta. So with 45 degrees, this is 1, so it will have the best launch. What's more, we have like the range, the maximum height and time expressed in times of b, that is initial speed. And as you can see, the range is 0.1019 times velocity to the square. Maximum height is 0.0246 times velocity to the square, and time is equal to 0.1417 velocity times velocity.
Sorry, can you just tell me what is that 0.02 and 0.14?
These were calculated with the formulas that Alberto. Yeah, we took like the angle that we established for catapult, that was 43 degrees, and with this angle we made the calculations, so we got this. But since we don't have like velocity, we left this with velocity as a variable.
Okay, so now the experimental procedure. Our experiment was rather simple, so it only consisted of 3 steps. The first is that we established a fixed angle, fixed initial height, and torsion. We wanted the launches to be rather similar and only change the mass. So we made sure that the building of our catapult would ensure that it was always at the same angle, and also at the initial height. And we ensured that the torsion was always the same by turning the pieces of wood that would create the torsion the same number of times in all of the lunges. This way, we would ensure that the force that was throwing the projectile was always the same, and therefore the initial speed was always the same still. We used 3 projectiles with different masses, which we're gonna get to the part later, but the masses were rather similar, so that kind of influenced our results. And then we filmed each launch and analyzed it in Tracker.
Okay, so here we use the Tracker software, and we arrange each of the moments that the ball or the projectile is launched. So here the software will make a average of each moment in time, the velocity, the position in x, and the position in y. So with these calculations, it is shown that the exit speed, that the magnitude of velocity, is 4 meters per second. And the initial position we already arranged it, so it's 0 centimeters in the x, supposedly, and the 60 centimeters of the height of this catapult. So we put it like that, and we have this metric measurement, so that the calculation in the pixels of the video will be all right. Then the exit angle that we calculate with this difference in velocities on the j and the x velocities is 43.9 degrees, so it's like very near the optimal 45 degrees. And we came across that the maximum height of the projectile is 1.1 meters, and the range of the total projectile is 2.5 meters, so it's like very similar. And the total height time of the object was 1 second. And this is the graphs here on the position of x, so it's incrementing, and this is the position in y of the object. So yeah, that's the most important piece of the data.
So now talking about the analysis and the calculations, theoretically, I think they already mentioned, we didn't have initial velocity, we couldn't calculate it because we didn't have the
torsion coefficient of the string that we were using. However, as you saw in the previous slides, we used like the variable d squared. So we had at the end like the calculations done, but without knowing the velocity, right? But with the experimental part, thanks to the tracker app, we could solve and calculate which was the initial speed, and without it was way easier to make the rest of the calculations. It would like basically evaluate everything. And since Fernand already mentioned, like the catapult was designed to have basically the same height, the same angle, and since the masses were pretty similar, the initial velocity was also pretty similar, and since the torsion force was like the same, in general the velocity was pretty similar one to another, and that's why the range and height were also quite similar, because the initial conditions were all basically the same, if we can call it that way. So without trackers, we wouldn't be able to see that.
Okay, so I know we have to like
Do we give like individual conclusions or
Okay.
general?
or just
Just like a very short, you don't have to read it.
Okay.
You can make a very
so
short
I
conclusion.
don't know.
Okay, so first we saw that actually drivers plays a really important role. Like we had our measurements, and what we did was to just link the formulas with an unknown initial speed, and then we calculated the initial speed, the real initial speed, and then we plugged that into our formula, and we realized that the calculations the tracker was giving us were still different to the ones that we had theorized. So even when we were using more real data, the calculations were still different because in our formula we didn't consider drag force. So we realized that it's a really important step when we're doing calculations in real life. And also we saw that torsion was the one that would also affect the range and the height, like because it could actually change like the initial speed. And so it was something that we really wanted to like take into consideration and was like the main focus of everything, so that everything would stay like constant.
And also like the errors that could happen in the construction of the catapult is also related with the rope, because the rope, when we are shooting these projectiles, with the friction, it could make the torsion lesser and lesser with different shots, so the results may change a little bit. But we also have a good estimate with the materials of the catapult, because we chose them right. But it could also affect because it could bend because of the wood isn't like as resistance as a steel material or aluminum material. So it's important thing to take into account in the next projects that we realize.
Also, our main experiment was the ones that we did for the airfare activity, which was with 3 different masses, but they were rather similar. But on top of that, we also did like another one with a ball. Like our 3 main objects were a marker, a piece of wood that was shaped in a triangle, and also a circular like cardboard like circular thing. So the drag force would be different in all of them because it relates to the shape. So we wanted to see how that worked. And we saw that with the ball, even though all of the conditions were the same, it still had like a major difference with the other one because it has a more aerodynamic shape. So it was a really big like change between the trees and the ball.
So this is the table of responsibility of each member of the team, and the reference.
References.
Thank you.
Just some questions. Yeah, because I didn't see any graphs of analysis in the presentation, so I would like to know, like, what was the major difference that you observed when you did analysis in Tracker and MATLAB? Maybe Luis can tell me.
Okay, well, the tracker, I think it was more accurate because it takes like the information from a real situation, the video. And in MATLAB, we need to use like a formula. We need to establish like the formula of the parabola and then like graph and make like with the Euler method or with the real parabola. So I think that the tracker is more accurate than the MATLAB.
And what about the initial positions, where it was starting with MATLAB and in Tracker? was the tracker was able to identify the initial position?
Well, I think yes, because also we could like modify it and we put like a metric, I don't know how to say it, like a metrica, so we could have like a reference to make it more accurate. That's why we think that, I think yes.
And also, do you remember we saw some problems without, mostly we did in the theoretical classes, we saw the situation without air resistance, and when we did simulation in Excel, we were considering the air resistance, right? So what were the differences in both cases, actually, in terms of formulas? Can you describe it?
In terms of formulas, well, first of all, I think in the Excel is something that I saw, like, noticed a lot, that we have to, like, kind of, like, concatenate, like, everything. But probably that's because of the structure of the Excel. But in the problems in class, the questions were really simple and, like, really short.
No, I'm asking about the parameters, like, in the formulas, there are changes in parameters, right? Because the acceleration changes and velocity changes depends on the considerations of their resistance and all. Then what were the parameters that we changed in the formula?
Well, like the most basic ones stay the same. But for example, when you consider a resistance, you have to consider like the shape, like that we never like really care about it when we were seeing like theoretical stuff. But here the shape affects. And for example, at the beginning I couldn't like quite understand what was the cross-sectional area. I thought it was like the area of all the superficial area, but it is not, something completely different. And also the density of the air, like then that means that in another fluid, in another fluid, the equation is gonna change even more than this. And we have, well, the drag coefficient also is something that we don't really care. Actually, we didn't see on the theoretical part, but when we have to do something practical, it's something that we have to consider because air is always against the movement, so obviously that's gonna affect all the motion of the object.
So, yes, Alberto? Okay. So, can you just tell me the steps, like what you did in MATLAB, like what were the steps?
Well, first we arranged the equation of the movement in the projectile with the drag force and the velocity. But when we are arranging that kind of equation in MATLAB, we have to put the guiding steps.
Sorry.
And, yeah.
Could we stop the film?
No. Yeah.
So yeah, we have to put the equation and the steps of each problem with the Euler method, and a change of the Euler method also changes the movement of the position and the velocity of our graph. So it's not as accurate as once putting in the MATLAB tells you, because the data recollection of the MATLAB is very different for the tracker, because tracker is just experimental, and with MATLAB it's just an approximation that could like make a difference between one step in the Euler method and other stuff. So it's like very difficult to put first the equation and then the Euler method and the steps and making the plot with the graph. So each graph is different, and we print it all in the file. So we see the like difference between each graph in the MATLAB. So yeah, it's like difference that could make a difference in a real experiment problem.
Okay. Fernando, can you just explain what he explained?
Yeah, okay, so like the same question, right?
Yeah.
Okay, so first we have to consider all the initial values. We have like the gravity, the density of the air, everything that has already explained for the formula. And then we had to use like a force to do the Euler method. But previously we had to do an activity in which we were changing like the steps. But now in this case we had to change the.
Actually, what is happening in Euler's method?
Okay, yeah. In Euler method is a method to approximate like the integral or something by using a derivative, because in this course we didn't see any integrals. So with the initial values in x and y, you can calculate the next value that will have like the solution, and then you can plot all of them, and that way you're gonna like kind of see the exact solution, but the accuracy of this method really depends on the length of the step. So the formula is like the y new value is equal to the y initial value plus like the step plus the derivative of y evaluated in the initial values of x and y. So we did all of that in a for, and then we had to consider the change in the drag force. So it was rather challenging. Actually, we were struggling a lot with MATLAB. We had to like do a bunch of different methods, because first we were trying to put everything in just one graph. But we had a problem because we had 4 different like drag coefficients, but we only had 3 initial speeds. So when we were checking our for, like for each drag coefficient, it was asking us for an initial velocity. So it was like something really mixed. So we had to change that code into 3 different codes, and then kind of section it so that we could have everything in one code. So we actually ended up doing like 3 different graphs, and in each graph there were 4 graphs with the 4 drag forces for each mass. And also we had to include an if, because the calculations were still being made, and in some cases the y equals 0 was already being reached. And we also had to like analyze all of that, because our initial height, like we had also a problem with that interpreter, because at first our calculations were showing that our height ended up being like negative, but it was because of the reference like mark. Our initial height was above the floor, but it was considering as it was 0. So we had to change all of that with a lot of ifs, and then do like each graph one by one, and then put the position that was like hold on, because we had a problem in each time a new graph was being made, they're like oscillating the other one. So overall it was like a big 4 for each drag force, and then it was a 4 to compute the Euler method, and the values of each of the Euler method were being stored in 2 vectors, one for the independent variable and another for the dependent variable, and then those values were being checked in MIF to see if it made sense like logically with the height and the range and everything, and then we would like graph everything, and we did that 3 times.
Okay, very good. So yes, now we can stop the record, and you can